Hey, I want to take a look at how to take the derivative of the product of two functions. In other words, suppose you have two differentiable functions, f and g. What is the derivative of the product f of x times g of x? And what you would really love would be for things to be so nice that the derivative of the product of two functions is just the product of their derivatives, like it was with the sum of two functions. Turns out this is not going to be the case, so don't get attached to this wrong formula. And let's see right now why it doesn't work. Take, for example, the functions f of x equals x squared and g of x equals x, so that their product is the function x cubed. Well, the derivative of x squared is 2x, and the derivative of x is 1. And so the product of their derivatives is just 2x times 1, which is 2x. On the other hand, we know what the derivative of x cubed is. It's 3x squared, and 3x squared is not equal to 2x, and so this rule just doesn't work. And so we're going to need to figure out what the derivative of the product of two functions is, and to do that we will of course use the definition of the derivative. And that definition says that the derivative of the product is the limit as h approaches 0 of the product evaluated at x plus h minus the product itself, all divided by h, so this expression right here. And you say to yourself, I wonder how I make any progress with this expression in order to do some simplifying to let me try to compute what the derivative is. Well, there are two standard tricks that show up over and over again in mathematics for manipulating an expression. And the two tricks are multiply by 1 or add 0, because you can always multiply by 1 or add 0, and that doesn't change the value of the expression. And in this situation, I'm going to use the add 0 trick, and in particular, this piece that I've added in the middle right here is a 0. It's negative f of x times g of x plus h plus positive f of x times g of x plus h. So that's 0. So I have exactly the expression above with a 0 added into the middle. And you might wonder why and how that's going to help, but that we'll see in just a moment. And how it at least begins to help is you'll notice that these first two terms here both have a g of x plus h in them, and so I can factor it out of those first two terms. Meanwhile, these second two terms right here both have an f of x in it, and so I can factor that out of the second two terms, and that gives me this next line right here, where all I've done is rewritten the line before with something factored out of the first two terms and something else factored out of the second two terms. All I've done here is split the expression into two fractions and then rewritten the fractions somewhat. For example, the g of x plus h that I have in the numerator here is the same thing as multiplying this whole fraction right there by g of x plus h, which you can think of as g of x plus h over 1. Same idea here, the f of x in the numerator, I can just multiply the rest of this expression by f of x and I get the same thing that I had, or something equivalent to what I had in the line before. I now apply the two limit laws that say that the limit of a sum is the sum of the limits and that the limit of a product is the product of the limits, and get this expression right here. And two parts of this expression are immediately recognizable. In particular here, the limit as h approaches 0 of f of x plus h minus f of x all over h. That's just the derivative of f. And similarly, this piece right here is just the derivative of g. You have to think a little bit about this piece right here, the limit as h approaches 0 of f of x. Well, f of x has no h's in it. As h goes to 0, f of x stays f of x. And then finally, there's this part right here, which is perhaps the most complicated of them all, not that it's difficult. The limit as h approaches 0 of g of x plus h. That does have an h in it. But if you recall, we started off by assuming that g was a differentiable function. And differentiable functions are continuous. We saw that where a function is not continuous, it's not differentiable. And so if it's differentiable, it has to be continuous. And what does that mean? That means that in order to compute this limit, all we have to do is plug in h equals 0. And putting that all together, we get our answer. The derivative of the product of two functions, f and g, is the derivative of the first function, f prime of x, times g of x, the second function, plus f of x times g prime of x. This is something that we call the product rule. The derivative of the product of two functions is the derivative of the first function times the second function plus the first function times the derivative of the second function. Let's see that it works in this simplest of examples that we started out with, where f of x was x squared and g of x is x, so that f of x times g of x is x cubed. This is a nice one because we know what the answer should be. Using the product rule, we get that the derivative of x squared times x is the derivative of the first, that's the derivative of x squared, which is 2x, times the second, and the second function is just x, plus the first function, which is x squared, times the derivative of the second function, and the derivative of x is just 1. And so that's 2x squared plus x squared, which is just 3x squared, which we happen to know is the derivative of the product of x squared and x, the derivative of x cubed. So at least in this one case, it works. And of course, it works in all cases. We computed it using the definition of the derivative and got a formula that will always work. Okay, you try this one. This is a nice one because you can check your work. So first use the product rule to find the derivative, but then do the algebra. In other words, compute x to the fourth times x cubed plus 2x and get a polynomial. Take the derivative of that polynomial and make sure that you got the same thing that you got when you used the product rule. So take a moment, pause the video, do all those little tasks, and when you're ready, start it up again and we'll burn through them. Okay, by the product rule, this is the derivative of this product is equal to the derivative of the first function. Well, the first function is x to the fourth and its derivative is 4x cubed, times the second function, so that's times x cubed plus 2x, plus the first function, that's x to the fourth, times the derivative of the second function, and the derivative of x cubed plus 2x is 3x squared plus 2. All that's left is to simplify, and after you distribute, you get this expression, and then combining like terms, you get this expression, the answer, 7x to the sixth plus 10x to the fourth. Let's check to see if we were right. Doing a little algebra, x to the fourth times x cubed plus 2x is x to the seventh plus 2x to the fifth. So if we do the algebra first and then take the derivative of what we come up with, then we very quickly see from what we've learned about derivatives of polynomials that the derivative indeed is 7x to the sixth plus 10x to the fourth. And you say to yourself, I don't like this product rule thing. I'll just bite the bullet and I'll always just do the algebra so that I can use rules for polynomials and simpler rules rather than having to use the product rule. Nope, sorry, it just doesn't work that way. Look at this one. Suppose we needed the derivative of x times e to the x. Well, there's no simplifying that. There's no algebra that you can do that will make that easier to work with. The only way you can take the derivative here is using the product rule. And so take a few moments, use the product rule, see if you can find the derivative of x times e to the x. Pause the video. When you're ready, start it back up and check your work. Couldn't really be easier. The product rule says that the derivative here is the derivative of the first, well, the derivative of x is just 1, times the second, and the second function is e to the x, plus the first function, which is x, times the derivative of the second function, and we know that the derivative of e to the x is e to the x. In other words, we just found that the derivative of x times e to the x is e to the x plus x times e to the x, and we couldn't have done it without the product rule. Okay, that was the product rule. When do you use the product rule? Whenever you have a product. You really have no choice. You saw what happened when we tried to take the derivative of the product of two functions without using the product rule. That was that x squared times x. That didn't work at all. You need the product rule if you're trying to take the derivative of a product. Okay, there's a homework on this stuff. Have some fun with it. See you soon.